Thanks for that. So my name is Lankhaar. I'm a postdoc at the Chalmers University of Technology and at the Leiden Observatory. And today I wanted to talk with you about spectral line polarization. In the first part of my presentation, I'm going to be talking about characterizing interstellar magnetic fields. And then towards the end, we're going to discuss characterizing chirality in the gas phase of the interstellar medium using spectral line polarization. So let's start talking about magnetic fields. And in order to do that, I'm showing you here, which is my favorite image in all of astronomy. This is made by the Planck telescope. I believe it's at 870 micron. And what we're seeing here is an image of the dust. And what you can see in this image is that it's drawn up almost like with faint brushstrokes, almost like it's been drawn up by Vincent van Gogh himself. And these brushstrokes, they're supposed to indicate a certain preferred direction in the emission that we're seeing here. And this preferred direction is the linear polarization. Linear polarization is produced by dust when it aligns itself, and this alignment is the alignment of the dust grains is with respect to the magnetic field. So when we're looking at this image, we're really looking at an image of the magnetic field of the Milky Way. And what we should notice in this image is that the magnetic field over large extents is coherent, which indicates that it is of dynamical importance to the gas flows on this galactic scale. And we know that magnetic fields also are important at smaller scales down to the stellar scale, important to the gas flows in astrophysical objects. Characterizing magnetic fields with the SKA and the ngVLA, you might think first about doing it with the radio continuum, for instance, with synchrotron emission or with Faraday synthesis. I want to talk about a technique that's I feel highly complementary to this, using molecular lines, because there we really trace the molecular medium instead of the diffuse medium. And what's more, we can use the velocity information that spectral lines hold. I've come all the way from Sweden to give this presentation. So this is the smorgasbord of line polarization. Line emission, I divide roughly into thermal lines and into maser lines. Thermal lines we can trace on scales of arc seconds, and they trace lower densities 100 to 1 million particles per cubic centimeter. Thermal lines are linearly polarized to about a few percent. So we really need all the sensitivity we can get. And the linear polarization traces the plane of the sky component of the magnetic field. Circular polarization for thermal lines occurs in paramagnetic molecules with an unpaired electron. And then we can trace the line of sight component of the magnetic field. This is through the Zeeman splitting effect. Now, the Zeeman, or the circular polarization, I should mention also, is inversely proportional to the frequency. So low frequency observatories are really important for this. Maser lines, masers are really point-like sources at milli-arc second scales, and they trace higher densities up to 10 to the power 12 particles per cubic centimeter. They're linearly polarized up to 100%, usually few percents, and circularly polarized, also a few percent, but up to 100% for the OH masers in galactic sources. Let's take the smorgasbord away. It's almost lunch, and I don't want to make you any more hungry. And we're going to start talking about linear polarization. I'm going to say a few words about the underlying theory, and then I'm going to give you some examples that are pertinent to the SKA and the ngVLA, which are not exhaustive at all and might have to do something with my biases in the science cases. So linear polarization in spectral lines is produced when the molecules that emit the spectral lines are aligned. Just the same mechanism as for the dust. And alignment is produced by an anisotropic radiation field. The mechanism of the production of alignment is very similar to a flag aligning itself in the wind. It's the same types of physics. The flag is interacting with a directional wind that aligns the flag. There's a similar principle when molecules are interacting with an anisotropic radiation field. The requirement is that we need non-LTE excitation. If collisions are present, they will scramble the alignment and you won't see any polarization at all. Polarization is in the levels of a few percent. Now I want to advertise this code portal, which treats all of the complicated molecular physics associated with these processes in a 3D polarized radiative transfer code that can translate an image like this. This is from ALMA to a magnetic field morphology. So the examples that I wanted to talk about, here we have the galaxy M33. These are SMA observations of CO. You can see the little white spots here. These are giant molecular clouds, which are seen in CO by Lee and Henning. And when these authors looked at the linear polarization of the CO emission, they saw that the linear polarization aligned with the spiral arms, just as the synchrotron emission does. These are VLA observations of ammonia towards a high mass star forming region, where the ammonia is seen towards the H2 region in absorption. And what I found very neat about these observations is that they really show the importance of the velocity dimension in the spectral line data, where they can see inflow and outflow in the ammonia data. And combining this with polarization observations will give you an information on the magnetic field as well, which is really a comprehensive image of the dynamics, the magnetohydrodynamics of a region like this. Let me say also a few things about masers, and for this I'm focusing on SIO masers. These are VLBA observations of SIO towards the evolved star TX-Chem, where the SIO is in a maser ring around the evolved star. And the SIO is excited right before the dust condenses and picks up the mass loss of this evolved star. And why I wanted to show this example is that the ngVLA can image this SIO emission at the same time as it images the continuum emission from the evolved star. So if you combine that with polarization images of the magnetic field, you really get a comprehensive image of the dynamics that is going on there right before the dust is formed. Let's talk about circular polarization. Then we're going to talk about the Zeeman effect. And I wanted to focus talking about the Zeeman effect on a phenomenon that is Zeeman broadening as well. So here we have Peter Zeeman. This is me very proudly with his bust. He actually grew up very close to where I was born. So one glorious afternoon, I drove to his bust and took this picture. And the Zeeman effect is the splitting of a spectral line in a magnetic field. And I like to say that Zeeman had a very easy time measuring his effect. What he did was he has control over the strength of his magnetic field. So he applied a very strong magnetic field to a spectral line. And he saw that the spectral line neatly splits up into the individual components. We astronomers have a much more difficult time. Our line widths are much larger than the splitting of the Zeeman effect. So we have to go to polarization to measure this effect. And usually what we do is we look at the circular polarization, where we subtract one emission group from the other, where one emission group is associated with right-handed circularly polarized emission and the other one with left-handed circularly polarized emission. So you get this V-shaped signal. What is often overlooked is that the splitting of the line also is associated with a broadening of the spectral line. And I made a little video illustrating this effect. We're going to look at the spectral line splitting up while the magnetic field strength gets larger. Then circular polarization is produced, but also the line is broadened. And the broadening of the line is quadratically proportional to the magnetic field strength, while the circular polarization is linearly proportional. This is an interesting fact, as you cannot trace, for instance, a turbulent component to the magnetic field with the circular polarization, whereas you can with the broadening. And where this effect is I feel mostly visible is in the Zeeman effect in protoplanetary disks. So this is a representation, a schematic of the radiative transfer of Cn in a protoplanetary disk TW Hydra. For protoplanetary disks, as all accretion disks, the toroidal magnetic field component, it changes sign through the midplane. So what we see in the circular polarization is a very much diminished signal, whereas the Zeeman broadening is not diminished at all, and it's a much more sensitive tracer to the magnetic field. Also, the linear polarization is quadratically dependent on the magnetic field strength, so it's much more sensitive to tracing the magnetic field. The Zeeman effect also occurs in masers. This is we're going to talk here about OH megamasers. These are Arecibo observations of the OH megamaser towards the LURG 3 Zwicky 35, where this is a very strong maser, and with the Arecibo you can see a very neat Stokes V profile from which you can derive the magnetic field strength. I wanted to include this example because we've had recent observations of another LURG, Zwicky 49, with Merlin. So these are interferometric observations. We can see that the OH megamaser is actually excited in a collimated outflow. So tracing the magnetic field dynamics of OH megamasers may shed light on the launching of this outflow and makes a very interesting object. So I also wanted to mention methanol masers. They're excited towards high mass star forming regions, and in the very inner regions, 100 to 1,000 AU from the protostar. It's a 6.7 gigahertz methanol maser excited, and it's also a very potent magnetic field tracer there. I think we're going to hop over these ones. I'm going to talk finally a little bit about detecting chirality in the interstellar medium. More than a few years ago, the propylene-oxide was detected with the GBT towards Sagittarius B2 in the northern part. And to me, this was a very exciting discovery as this is a chiral molecule, and it opens up the possibility to look if one of the enantiomers is there in a higher abundance. Life on Earth is distinctly homochiral, and this homochirality has already set in the gas phase of the interstellar medium. Here you can see the observations. These are from the GBT. So propylene-oxide is seen in 3 transitions. And in order, to look if propylene-oxide exists in the interstellar medium with one enantiomer more than the other, you look at what is called, an effect is called circular dichroism. This circular polarization in the emission lines. And you can estimate the circular dichroism, the circular polarization fraction due to the circular dichroism through this formula. It's basically a ratio of the magnetic moment of the transition with the electric dipole moment of the transition. And this effect produces then circular polarization if you have a non-racemic mixture. So we calculated this factor to look what kind of polarization fractions do we expect if we have a non-racemic mixture here. Unfortunately, the expected circular polarization due to the chiral asymmetry is of the order of parts per million, less even, for a line like this. So while I'm very impressed with the sensitivity of SKA and ngVLA, we're not going to see these types of polarization fractions. What we can do instead, however, is look at a radical species, a radical chiral molecule, and then for a radical chiral molecule, we would expect polarization fractions of the order of 1%. So we should be able to see that with these new instruments. I'm going to leave up my summary slide here, and thank you for your attention.
right, thanks very much. And do we have any questions? Oh, we have several. Yeah. These two over here. Yeah.
Hi. I'm Dao Chongqing from NRAO. So I have one question and one suggestion. For the Gorak Kalafas effect, the polarization could be perpendicular or parallel to the polarization. How could you solve this ambiguity?
You can solve that ambiguity through radiative transfer modeling. I showed you that we possess over a code, which is the portal code, which can model the radiative transfer in an astrophysical region. We can do that. So it can model the anisotropic radiation field, which give rise to the Goldreich-Killifish effect. And also can tell you if the polarization is oriented perpendicular or parallel to the magnetic field. So,
okay. And also for the Zeeman, actually, the magnetic field on the plane of sky can also generate linear polarization.
That's right.
Could you consider it with the SK or ngVLA sensitivity?
Yeah. So. So the linear polarization is produced through the Zeeman effect. One object I showed you was the protoplanetary disks. I feel, or from my calculations, linear polarization is produced to much higher degrees than circular polarizations in these objects. However, for other astrophysical objects, I'm not too sure that linear polarization will be higher. And since we already have a hard enough time to trace the circular polarization, it's going to be difficult.
Thank you.
Okay, there's a question in the next row there. Yeah.
Hello. Hi. First of all, I'm not an expert in this field. I'm very curious in terms of measuring the turbulent magnetic field using the line broadening. Do you have any comments how feasible we can actually use this technique for the extragalactic star forming region?
Well, I never did it for a galactic one, so that's one part of the answer. It depends on the tracer. It depends on many factors. Again, the protoplanetary disk, I feel is one object that can really serve as a proof of principle here. And after we've done that, then we can look at molecular clouds. You need thin lines, or you need narrow lines. You need lines at high angular momentum. Yeah, so then you can start to see the Zeeman, and of course you need an observational. You need an instrument that has very good spectral resolution as well, so that you can measure the line width at the high fidelity. But I cannot, from the top of my head, give you like exact numbers here.
Other questions? So can I ask one? So thermal polarization, at the beginning you showed sort of which molecules are, give you the line of sight, which give you the plane of the sky, and they're usually different molecules.
Yeah.
So are you optimistic that with SK and ngVLA we might actually see some overlap at all in the molecules or in the critical density of those molecules that would allow us to measure the full magnetic field?
Mm-hmm. I think so. Yeah. The molecules are not over. Oh, we have it here. They're not overlapping because I only put out the selection of paramagnetic molecules there. But in principle, for the Goldreich-Killifish effect to operate, there's no requirements that there has to be a non-paramagnetic or a paramagnetic molecule. So it could be that they are in the same traces, but. So yeah, from that you can get the 3D magnetic field. That would be possible.
That would be great. Any more questions? If not, let's thank our speaker again. Thank you.